Hey there, Adam.
Hello, Henry.
I have the power!
All right. This lecture is going to be a very brief lecture over the concept of power. Now, this is going to finish off the energy unit. And so, and it's not going to take very long to explain because power is something that we see every day. We see it in automobiles, we see it in light bulbs, we see it in electricity, we see it in our lawnmowers. Anything with a motor, we have this idea of power. Electrical motors, anything. What is the power? Well, power describes the rate at which an object or a machine can do work. All right, and in this case, because we're talking about mechanical energy, we're going to just go ahead and just specifically say that it's mechanical work. So the rate. And so if I look at this, let's go ahead and start highlighting some things. It says the rate. Rate implies a time part. So rate implies this time interval delta t. And then we have this idea of work, which is W. And so I could say that power equals the rate at which work is done. So the amount of work over a given time interval. All right, and the variable for power is P. And so let's go ahead and draw a box around this so that we can keep it. And that's going to be the equation for power. See, look, we're almost done. That's simple. So whenever I look at this, there's some things that I need to know, such as, well, what are the units of power? The units of power are what? And this is a funny joke, except it just doesn't convey as funny as being as funny whenever I do it over the computer. But it'd be something like this. So, what's the unit of power? And then you should say, what? And I'm like, no, I'm asking you. And then you'd be like, what? And then be like, no, I'm telling you. Yeah, see, so it's not so funny over the computer, but the units of power are watts. All right. Now, if I look at this, there's some things that I can come up with, such as, notice how it doesn't say that if a machine is so weak, it can't do work, or if it says the machine is so strong, it's going to do too much work. Instead, what it's saying is it's saying that if I have a weak machine, and so let's go ahead and compare two machines that have two different power ratings. Let's say I have machine 1 with a power of the machine 1 of being 100 watts, and the power of machine 2 being 10 watts. And let's say that I have to lift a block. Let's make it a pretty block. Let's make it a heart. Look at this. We're going to lift a heart in sake of Valentine's Day. And I want to lift this heart with a displacement up. And so my force vector, we'll go ahead and make my force vector red, and the displacement vector blue. And let's just say that my force equals 10 newtons, and my displacement equals 1 meter. And so the work done, which is F delta x equals work, and so the force is 10 newtons times 1 meter, which gives me 10 joules of work. So I'm going to lift this heart up in sake of Valentine's Day, and it's going to be 10 joules of work. Now I have one machine that can do 100 watts, or it's a 100 watt power rating, and another machine that has a 10 watt power rating. And so if I were to look at this, where power equals work divided by delta T, well, the machine with, let's go ahead and do some rearranging. So if I rearrange this, then I have power times delta T equals work. Oh, wait a minute, that's not what I wanted to do. Let's erase real quick. I want to solve for delta T. That's what I'm looking for. So let's see here. If I want to solve for delta T, well, I'm just going to switch positions of the P and the delta T. And so I get delta T equals work divided by power. And so they both have to do 10 joules of work. So 10 joules of work. And then let's look at the first machine, 100 watts. Now 10 divided by 100 is 1/10. So it's going to take 0.1 seconds to complete the 10 joules of work. Whereas if I look at delta T equals, and in this case, 10 watts, so that's going to be 10 joules divided by 10 watts. Well, that's going to take 1 second. So even though this machine is substantially, or has a tenth of the power as the first machine, it can still do the same amount of work. It just takes it longer to do that. Now there's another derivation that I want to look for this power equation. All right, and it says power over here equals work divided by my time period. And so if I look at what the equation for work is, so power equals work divided by delta T. Well, work is just my force vector times my displacement vector all over delta T. So let's see here. I have seen delta X divided by delta T before. Can anybody tell me what that is? Waiting. Well, yeah, that's what it is. Delta X divided by delta T is just the velocity. So I can rewrite the power equation as force times velocity equals power. And this is another equation that we are going to use to calculate power. And this is actually means quite a bit. It means that the force required to keep an object traveling at a certain velocity equals the power. So if I wanted to continue or to push an object with a velocity of 3 meters per second, so V equals 3 meters per second. And let's say that in order to do that, I have to apply a force equal to 5 newtons. Well, that means that the power that I have to exert, or the power rating of a machine that is pulling that object, is going to be 15 watts. Okay, and so that's the implication that this has. And so now I can use a velocity and a force to come up with the power, as well as the work divided by the time period to come up with the power. All right, now I want to look at an example problem. And so this is actually one out of your book. Your homework, by the way, is going to be, or for this section, is page 189, 1 through 5, or 2 through 5. I'm working number 1 right now. So this is page 189, number 1. And it says I have a 1 kilogram elevator, or a 1,000 kilogram elevator that carries its maximum load of 800 kilograms. A constant frictional force of 400 Newton retards the elevator's motion upwards. What is the minimum power in kilowatts must the motor, or what is the minimum power in kilowatts must the motor deliver in order to lift the loaded elevator at a constant speed of 3 meters per second? So let's go ahead and start highlighting some things. Let's pull out this green highlighter. I know that the mass of the elevator is 1,000 kilograms, and the mass of the load is 800 kilograms. All right. I also know that there is this frictional force involved of 400 newtons. All right, and it says that it retards the elevator's motion upwards. Now this word retards means slows down, so it's actually opposing the upwards motion of the elevator. All right, it says what is the minimum power, so that's what I'm looking for. That's my question. And I want to lift the elevator at a constant speed of 3 meters per second. So let's go ahead and write my knowns. Well, I know that the mass of the elevator and load, I'm just going to go ahead and put those both together. Well, it's 1,000 kilograms plus 800 kilograms, so it's going to be 1,800 kilograms. All right. I also know that there is a frictional force, the force of kinetic friction, and I know it's kinetic because the object is moving, of 4,000 newtons downwards. Okay, and I know I want to lift with a velocity equal to 3.00 meters per second. And then I'm looking for power. Now, one thing about this problem is that we have to go back to the force chapter, and we have to look at the free body diagram, which I have drawn here. I have the force of friction, which is the blue line, F sub k. And then I have the green line here, which is the force of gravity. And then the red line, or the red vector, which is the force applied by the motor. Now, in order to figure out power, the power of the motor is going to equal the force of the motor times the velocity, okay, using the P equals FV equation. So I need to figure out this force applied. All right. In order to figure out the force applied, I have to look at this velocity, and then it says that it's a constant velocity. Now, the constant velocity means that the net forces on the elevator are going to be zero because it's not accelerating, and so the net force is zero. So if I were to look at this, well, then I could say that the force applied is actually going to equal, well, the force of kinetic friction plus the force of gravity. All right. Well, it's given me the force of kinetic friction. It's 4,000 newtons. And the force of gravity, well, we need to look back at that chapter also, and I'm going to write that equation over here where the force of gravity equals mass times the acceleration of gravity. So in this case, 1,800 kilograms times 9.81. And so the force of gravity equals, let's go ahead and pull up the calculator. Go gadget calculator. I'm going to do it the hard way, I guess. My quick keys aren't working that well. So if I look at this, I want to take 1,800 times 9.81, and I get a force of gravity of 17,658. And let's go ahead and just keep two significant digits because my 1,800 here only has 2. Actually, I think that has 4, and that number has 4. And the 9.81 only has 3. So let's just stick with 3 then. So 17,700. So my force of gravity is 17,700 newtons. All right. So the force of kinetic friction is 4,000 newtons plus the force of gravity, which is 17,700 newtons. And so my applied force, F applied, is going to equal 21,700 newtons. All right. So now that I've made it to this point, now it's just a matter of plugging this number into our equation right there, because that's the force from the motor. That's our applied force by the motor. And so let's see here. The power of the motor equals 21,700 newtons times our velocity, which is 3. Pull up my calculator again. 17,700 times our velocity, which is 3. And so that means that my power rating must be 53,100 newtons, or 53,100 watts. So the power of the motor has to equal 53,100 watts. All right, so now I figured out the power in watts. This asks me in kilowatts. Well, there are 1,000 watts in 1 kilowatt. That's what the kilo stands for. And so that means that the power of the motor in kilowatts is just 53 kilowatts. And there's my answer. All right, so I'm having to bring in some stuff from the old chapter. Hopefully, we haven't totally forgot that information, because one thing about physics is that it consistently builds on each other.
Wow, Stewie, you look like a new man.
Well, will you look at me? I have the power!